So in this video, we're going to talk about how to do the uncertainty calculations for this made-up data. All right. So the gliding along lab, how do we do uncertainty? So if you remember, uncertainty is like how close is our measurement. So the closer your measurement is, the smaller the uncertainty. So let's talk about this. Remember this data table we made? So the displacement was 1 meter, then 2 meter, then 3 meter. That's how far the puck went over time. And then we did 3 trials, trial 1, 2, 3, and then we took the time of each trial. So the time for trial 1 to get to the first meter was 0.5, then trial 2 was 0.6, trial 3 was 0.7, etc. Right? We averaged the total times, and if I were to ask you a question, how much time did it take this puck to get to the first meter? And you would say 0.6 seconds on average, but was it exactly 0.6 seconds? The answer is no. And what we need to do is we need to include an uncertainty statement or uncertainty. So we're going to put plus or minus, meaning that it's not exactly 0.6 seconds, but if I add like a range of values it could be, I know it's going to be between that range. And for the average total time, what we're going to do is we're going to try to find out what's the farthest away that our data was from the average. So then we look at each trial. We're going to look at trial 1. How far away was this one from 0.6? Our first trial was 0.1 seconds away from 0.6. Because it was 0.6 minus 0.5, this is 0.1. That was 0.1 seconds away. This trial, how far away were we from that one, from our average of that one? Well, that one was 0.6, our average was 0.6, so we were spot on. We were exactly at 0.6 for that one. This one, we were also 0.1 second away. So 0.7 minus 0.6 is 0.1. So this trial and this trial, we were off by 0.1 seconds. So we can say to our whoever we're presenting this to, and say, all right, the time it took for that puck to get to that first meter is 0.6 seconds, but we could have been off by 0.1 seconds on any given trial. So I'm going to put that, plus or minus 0.1 seconds. So this is the story we could say. How long did it take for the puck to get to the first meter? It took about 0.6 seconds, but plus or minus 0.1 seconds. It's within that range. So that's what we'd write, 0.6 plus or minus 0.1. We're going to do the same thing for this trial. The average was 1.4 seconds. So it took an average of 1.4 seconds to get to the second meter, but if you look at each trial, none of them were actually 1.4 seconds. So what we need to do is we need to look at, okay, how far off is this one? Well, 1.4 minus 1.2 is 0.2, right? And this one, 1.5 minus 1.4 is 0.1. And then this one, 1.6 minus 1.4 is 0.2. So if you look at each of these, this one was 0.2 seconds off, this one was 0.1 seconds off, and this one was 0.2 seconds off. The farthest off that we were was 0.2 seconds. So we're going to put that. We're going to put the farthest, the maximum deviation from the mean. That's what it's called. So the farthest off that we were is 0.2 seconds. So we can tell this to whoever's reading our data, say, all right, how long did it take for that puck to get to the second meter? 1.4 seconds plus or minus 0.2 seconds, meaning that we could be plus 0.2 seconds or minus 0.2 seconds from that value, and all of our data fits in within that range. Finally, the last one, we're going to do it quickly. This one's 0.2 off, this one's 0.1 off, this one's 0.2 off. So we're going to say, all right, the farthest off that we were is 0.2 seconds. So it took an average of 2.7 seconds to get to the third meter, but it might be 0.2 above or below that. And we could say that to whoever's reading this data, and they would say, oh, all right, our data is pretty good because we were only off by fractions of a second. Now going back to displacement, there's also uncertainty in our measurement and displacement. Was the puck exactly at 1 meter when it got to that tape? And the answer is no. We don't know that it was exactly 1 meter, 1.00000 meters. But we can say that it was within a range. Now if you notice this puck, this is the puck that we use. Let's say this was the line right here, this line right here. And this is the 1 meter mark, all right? As the puck was moving along, did we stop our timer when it got to here? To here? To here? To here? That's a big difference because depending on where we stopped our timer or detected that 0.6 seconds is a big difference. Where was that puck exactly? Was it right in the middle, or did it just pass the line? It's hard to tell because we did it from the video. All right, so what we could do is we could add a little bit of error in the distance. And what I'm going to use is I'm going to use the error of half this puck. Meaning like, all right, if the puck is in the middle, then we're only off by half a puck. If the puck is at the end, then I could have guessed half the puck. So if you are measuring something with an instrument, you always go half of the smallest increment. And we're going to go half of the puck because that's the distance that we measure. We measured the length of this puck. And that's about 3 centimeters, which is 0.03 meters. So I'm going to add that on to each one, 0.03 meters. So we could be off by 0.03 meters on each of those distance measurements. All right. Interval time. So the rules for uncertainty. There are 2 rules for uncertainty. I'm going to go over those now. So pause. Rule 1 for uncertainty. If you add or subtract 2 measurements, then you simply just add the uncertainties together straight up. The second rule for uncertainty is if you multiply or divide 2 measurements, then you have to add the fractions or percentage uncertainties together. So here are a few notes to remember as you're working through this. Always do the measurements in the calculations first. Okay? So you either add, subtract, divide, multiply those measurements up, leave uncertainty alone. For me, it always is helpful just to do the measurement calculation first and then worry about uncertainty later. Then do the uncertainty calculations after that. Uncertainties always add up. Always add up. This is because if you have an error in one measurement and an error in another measurement, measurement 2, what ends up happening when you combine those 2 measurements is that those 2 small errors will grow into a larger one. And they'll keep growing and growing. So the only thing to remember is the following. So let's say you multiply or divide 2 measurements like velocity, where you have meters divided by seconds, then you have to do something different. You have to convert your uncertainty to a fraction or percentage before you can add them together. So as an example, let's say we wanted to find the percent uncertainty interval velocity. Remember, interval velocity was just interval displacement over interval time. So what we need to do is take the uncertainty in interval time divided by interval time, because that's the percentage uncertainty, and we add it on to the percentage uncertainty for interval displacement, which is the interval displacement uncertainty divided by the interval displacement. Remember, percentages is just a part divided by the whole, and uncertainty would be the part, whereas the measurement itself would be the whole. So what we're doing is we're adding the fractional or percentage uncertainty in time, and we're adding it to the fractional or percentage uncertainty in displacement, because those are the 2 measurements that we made. And since we're dividing the 2 measurements, we have to add the fraction or percentage uncertainty together. Good. So now that we know the rules of uncertainty, let's apply that to interval time. So interval time is basically the amount of time between 2 intervals. So we started our timer at 0, and we went to the first interval, which is 0.6 seconds, or 1 meter. All right. So if you look at this, the 0.6 seconds, it's not exactly 0.6 seconds, it's 0.6 plus or minus 0.1. So I'm going to write that. That was what our time was at that first meter. It wasn't 0.6, it was 0.6 with some given error. All right. So this is our uncertainty for that first displacement, our first meter displacement. Now, what we had to do is we had to subtract off our initial position, which was 0. So we're going to subtract off 0 here, and this doesn't change. If you subtract off 0, it's still 0.6. And there was no uncertainty at our initial point because we knew exactly where we started, so that doesn't change. So the first one's easy. All right. The next one's tricky. How did we get that 0.8? Think back to how did we get that 0.8? We got that 0.8 by taking 1.4 minus 0.6, because it was at 0.6 seconds at 1 meter, 1.4 at 2 meters, so we subtracted 2 values. So we got that 0.8 by taking this number and subtracting that number. So I'm actually going to just work through the math here with you. We're taking 1.4, but it's not exactly 1.4, it's 1.4 plus or minus 0.2, and we're subtracting off this number, 0.6 plus or minus 0.1. All right, so the rules for uncertainty are this. We take the values, the measurements themselves, and we just do whatever it tells us to do. Here, we're taking 1.4 minus 0.6. So the measurement itself, we just add, subtract, whatever this tells us to do, that's what we do. So 1.4 minus 0.6 is 0.8. Then we look at our two rules for uncertainty. Here they are again. All right. It says if you are adding and subtracting two numbers, then you simply just add the uncertainty. So here's the uncertainty for the first one, 0.2. Here's the uncertainty for the second one, 0.1. I have to add those together because anytime you have two measurements, the uncertainty is going to grow and grow and grow for each measurement. If you're off by one measurement, off by another measurement, the uncertainty is going to get larger. So 0.2 plus 0.1, even though we're subtracting here, we have to add the uncertainties. Uncertainties always add. Uncertainties always add, all right? So plus or minus 0.3. All right, so uncertainty grew because we took two measurements and we got an uncertainty even larger because each measurement was a little bit off. So those two small errors add to a bigger error. That's one way to remember it. How do we get this 1.3? Well, we got to 1.3 by taking this number and subtracting off this number. So I'm going to show you that math here. We took 2.7, but it's not exactly 2.7, it's plus or minus 0.2. And we subtracted off this number, 1.4 plus or minus 0.2. All right, the 2.7 minus 1.4, just do the measurements exactly what it tells you to do. We subtracted them, so it's 1.3. But then, remember, we have to add uncertainties. Add uncertainties, so 0.2, 0.2, this one's 0.2 off, this one's 0.2 off. Add those together, it makes 0.4. So we could be off by 0.4. Those uncertainties grow. All right, almost done. Last column, interval velocity. We're going to do the same process here. We're going to look at the rules for uncertainty and try to figure out what those uncertainty things are. So I'm just going to tilt this a little bit this way. All right? So, interval velocity. How do we get this 1.7? Well, what we did is we took our interval displacement, which is that, took an interval displacement, and we divided by our interval time. All right? So let's do that. All right? So we took our interval displacement 1.00, but it's not exactly 1.00. It's 1.00 plus or minus 0.03. And we divided by our average total time. Oh, sorry, our interval time, which was 0.6 plus or minus 0.1. All right. Now the rules for uncertainty are this. The measurement itself, you just divide, multiply, add, subtract, whatever it tells you to do. You just do that to the measurement. So the 1.0 divided by 0.6 is 1.7. We did that already. The measurement itself is 1.7. But for the uncertainty, the two rules are if you add or subtract two measurements, then you just add the uncertainty. If you multiply or divide measurements, then you have to add the percent uncertainty. So what we need to do is, these are not in percentages. 0.03 and 0.1 are not percentages. You have to change them to percentages. And the way you change them to percentages, just like any percent, is you take the part divided by the whole times 100. So this 0.1 is a certain percentage of 0.6. So the way you get that is 0.1 divided by 0.6 times 100. 0.1 divided by 0.6 times 100 is 17%. So I'm going to change that. Instead of saying 0.6 plus or minus 0.1, it's 0.6 plus or minus 17%. All right? I'm going to do the same thing for the top. I have 1 plus or minus 0.03. The way to change that 0.03 into a percentage is I take 0.03 divided by 1 times 100, and if you do that, you get 3%. So this is the same thing as saying 1 plus or minus 3%. All right? So this measurement is 3% off. This measurement is 17% off. So our total measurement, remember you add those together, is 17 plus 3 is 20% off. So we could say at that first meter mark, how fast is the puck moving? It's moving at 1.7 meters per second, but it might be 20% faster or 20% slower than that. It's not saying it's 20 meters per second faster, 20 meters per second slower. It's saying it's 20% more or 20% less. So your goal is to do that for your data. I'll maybe do one more for you here. How did we get that 1.3? Well, we took 1.3, it would be our interval displacement, which is still 1. 1 plus or minus 0.03. And we divided it by our interval time, which is 0.8 plus or minus 0.3. All right? And what we have to do is we have to change these two percentages. So the 0.03, the way to get that to a percentage, it's 0.03 divided by 1, the thing it's measuring, times 100. So that just changes to 3%. Woo! Lights went off. All right. 3%. So it's 1 plus or minus 3%. This 0.3 is a certain percentage of 0.8. The way you get that, it's 0.3 divided by 0.8 times 100. That's 38%. So this is 0.8 plus or minus 38%. And so our final answer would be, all right, let's look at joules. 1 divided by 0.8, that's 1.3. That's the speed in meters per second. But we might be plus or minus a certain percentage off. We always add uncertainties. Here's the uncertainty. It's 3% off on this one, 38% off on that one. When you add those together, it's 41%. Now, I did make some notes for you. You can check out the notes. And also, feel free to ask questions on how to do the uncertainty calculations. This is probably the hardest part of the lab. So if you get stuck, feel free to ask. And I'm here to help you. But if you can get through this, the rest of the lab is cake. It's breezy, all right? And just stick with it, and you'll do fine.